Okay, so the last section that is going to be on our chapter 4 test is section 4.7, and it's L'Hopital's rule. So what this theorem is essentially saying is we're going to have some ratio, and when we're taking the limit of that ratio, we're going to end up with an indeterminate form. Okay, and so what an indeterminate form is, it is when you get indeterminate either 0 over 0 or infinity over infinity. Okay, so as we learned, I think it was chapter 2, we were doing limits like crazy. And we learned a bunch of different techniques to evaluate them. So with this section, what we're going to do is we're going to learn a new rule that happens when you have this scenario come into play. And when this comes into play, what we can do is we can take the derivative and then evaluate the limit. So it just gives us another tool in our tool belt to solve these problems. So let's go ahead and start with an example. So in this example, the first thing that I'm going to do is I'm going to directly substitute in 1, because that's the value that this is going to. And if I do that, two times 1. I'm going to end up getting 0 over 0. Okay, so that's not doing me any good. So what we're going to do is we're going to take the derivative of both the numerator and the denominator. And you're doing this separately, okay? So we're not doing the quotient rule in this case. So I'm going to get 3x squared plus 2x minus 2 over 1. And now what I can do is I can directly substitute in my 1 to evaluate this limit. All right, so if I do that, I am going to end up with 3 over 1, which that can just reduce down to 3. Bada bing, bada boom. Wasn't that fun? Okay, let's do another one. All right, so this one's a little bit more complicated when I'm taking the derivative, but let's see what we got going on here. So when I plug in 0, I'm going to end up with so essentially we're going to have 3 minus 3, which is 0 over 0 again, okay? All right, so let's go ahead and take the derivative. So in this case, we're going to have a bit of the chain rule, right? So for this part right here. So I'm going to say that u is going to equal 9 plus 3x. So that would give me the derivative as 3. And then I'm going to say that u to the 1/2, and I'm going to take the derivative of that. So I'm going to end up with 1/2 u to the negative 1/2. So we're going to end up with 3 from this in my numerator, 2 in my denominator. This is going to drop down because the negative exponent. So we're going to end up with the square root of 9 plus 3x. Okay. All right, so we're going to end up with that. And then if I do, let me switch colors. The derivative of x is just going to be 1. All right, so now let's write all of that down. So this is my derivative of my numerator, and my derivative of my denominator is just going to be 1. So in essence, what I can do now is I can just take the limit of this as x goes to 0, and I'm going to end up with 3 over 2, 9 plus 3 times 0. So that's going to give me 3 over 2 times square root of 9, which is 3. So square root of 9 is 3 times 2 is going to give me 6. So 3 over 6, which is going to be 1/2. All right. That was fun. Okay, let's do another one. Ooh, trig. I hear the groans through the computer. Okay, so if I plug in 0 for this, I'm going to end up with evaluating the tan at 0. Ooh, that was really sloppy. Okay, so if I'm looking at my unit circle, I know that the coordinate here is 1, 0, and we know that tangent is sine over cosine, which is our y value over our x value. So in essence, when I do this, I'm getting 0 over 1 over 0 over 1, and that is going to end up giving me 0 over 0. Okay, so we're going to take the derivative, and in this case, we're going to end up doing the chain rule again as well with what is inside the parentheses. Okay, so I'm going to say that u, wow, that's a very sharp u. Okay, so u is going to be 4z. Okay, so then my derivative is 4. And then we got to think about the derivative of tangent. So the derivative of tangent is secant squared. So then I'm ending up with 4 secant squared 4z. And so then the bottom is going to do the same exact thing, okay, except it's going to be 7 instead of 4. All right, so let me write all that down. So my numerator is 4 secant squared 4z, and my denominator is 7 secant squared 7z. All right, and we're evaluating this limit as z goes to 0. Okay. So in essence, what we need to think about is we are going to end up plugging in 0 for our z. So this and this are going to be 0. So then we have to figure out what is the value of secant at 0. And so what you need to remember is that secant is essentially the same as 1 over cosine. Okay, so then what is the cosine value at 0? Well, that's our x, so that's going to be 1. So essentially, when I substitute in 0 and I evaluate secant squared at 0, I'm going to end up with 1. So then 4 times 1 over 7 times 1 is going to give me 4/7. And if you're forgetting a little bit about your unit circle, the front of your textbook does have a unit circle for you to reference. Okay. Let's do another one. Okay, this one's going to be interesting. So start by plugging in and seeing what we get. Okay, so you probably remember me just saying this. Secant at 0, since secant is 1 over cosine, is going to be 1. So this is 1. So essentially we're getting 1 minus 1 over 0, which is 0 over 0. Okay, so that's not good. All right, so let's go ahead and do our derivative of our numerator and our denominator. Okay, so the derivative of secant is secant x tan x. And the derivative of 1 is it's constant, we don't care. And then the denominator is going to be 2x. All right, so now let's go ahead and try to take that limit again. Are you seeing the problem here? So now we're going to do secant of 0 times tangent of 0, all divided by 2 times 0. Ooh, do you see the problem? Okay, so we know that secant of 0 is going to be 1. Tangent of 0, tangent, remember, is sine over cosine. And if we have our unit circle, this point, remember, is 1, 0, and sine over cosine would be 0 over 1. So 0 divided by 1 is going to give me 0 for my tangent, and that's going to be divided by 0. So I'm ending up with 0 over 0 again. So guess what? We're going to do L'Hopital's rule again. What? Yeah, okay. So this time, since our numerator has a secant x and a tan x, we're going to end up doing the product rule. So the derivative of secant is secant x tan x. And the derivative of tan is secant squared x. Okay, so I'm using that so I can reference it when I write down my product rule. Okay, so remember when you're doing your product rule, it's the derivative of the first one times the second part normal, and then the derivative of the second part times the normal first one. Okay, so I'm going to end up with, I'm going to start with this one. So secant x tan x times the normal tan x. So this is the derivative of the first one times the normal second one. Plus, okay, now I'm going to do the first normal one times this derivative. So we're going to get secant x times secant squared x. Okay, and that is going to be divided by the derivative of the denominator, which in this case now is going to be 2. Okay, so I'm going to clean this up just a teeny tiny bit because there's a lot going on here. So we have essentially secant x tan squared x plus secant cubed x. Okay, that's much prettier. All right, so now let's try the limit again and see. Hopefully we get something a little bit better. Okay, so let's look at our pieces individually. So we know secant x is 1. Oh, I wanted to switch colors. Hang on. Okay, so this is 1. And then tangent, we know that that is 0. So it's not going to matter that it's squared because it's going to be 0 times 0. All right, so essentially for this first part here, we're doing 1 times 0. And then secant is 1. And it doesn't matter that there's 3 of them because 1 times 1 times 1 is still going to be 1. So we're going to end up with 1/2. Yay. Isn't this so fun? Okay, so let's do the next one. All right. All right. So I think, what? Did it? Yeah, there we go. Okay. So let's go ahead and work through this next example. So if I substitute in 2 into my numerator and my denominator, I'm going to end up getting 0/0. Okay, so let's go ahead and apply L'Hopital's rule and take the derivative of both the numerator and the denominator. So I'm going to get 3x squared minus 6x all over 4x to the third minus 12x squared plus 14x minus 12. Okay, so then I'm going to evaluate the limit as x goes to 2. So I'm going to directly substitute in 2, and I'm going to see if I get something besides 0, 0. Okay, so unfortunately, when I plug this in, I get 0, 0 again. So that means we're going to apply the rule again and take the derivative again. Okay, so if we do that, we're going to end up with 6x minus 6 over 12x squared minus 24x plus 14. So let's try the limit this time. And we're going to end up this time with 6 over 14, which can reduce down to 3/7. Yay! Okay, let's do another example. All right, so if I substitute in 0, I'm essentially evaluating sine at 0. And sine at 0, remember on our unit circle, that's going to be 1, 0. So sine at 0 is 0. So even though it's squared, 0 times 0, it's not going to matter. So we're going to end up with 0, 0. Okay, so let's go ahead and apply L'Hopital's rule. And when we're doing this, we're essentially going to have to do the product rule for our numerator and the chain rule. So sine squared 3x is essentially telling me that I have sine 3x times sine 3x. Okay, so I would need to do the chain rule for 3x inside here. And if I took the derivative of that, I'm just going to get 3. So what essentially I'm going to do is I'm going to take the derivative of sine u, and that's going to give me cosine u. And the derivative of my 3x is 3. So essentially this is going to turn into 3 cosine 3x. Okay, so remember for your product rule, you do the derivative times normal plus normal times the derivative, right? So we're going to end up with, in total, 3 cosine 3x times sine 3x. And then we're going to have another one because we're multiplying by the same thing. So 3 cosine okay. All right, all divided by, in this case, 2x. All right, so let's clean this up a little bit before I try to take the limit. So essentially, I'm ending up with 6 cosine 3x sine 3x. okay, all over 2x. All right, so you might be seeing the problem that we still are going to have. So the denominator is still going to end up being 0 because 2 times 0, okay? So that's a problem. And actually, the numerator is going to end up still being 0 because sine of 3x is going to be sine times 0, which is 0. So I don't even care that this is going to be not 0, because 0 times anything is going to give me 0. So again, I'm getting 0 over 0, which means we're going to apply our rule for a second time and see if that makes a difference. Okay. So we're going to have to take the derivative again. And in this case, I've got two things. I'm going to factor out my 6, okay? So I just want to be looking at the derivative of these two pieces. So we are going to need to do the product rule again. And so essentially, when I have my cosine 3x, we already have been discussing the fact that we essentially have to do the chain rule because it's 3x, but it's not that tricky because we're just going to end up multiplying by the 3, right? So the derivative of cosine is negative sine, and we're going to multiply that by the 3 that I get from taking the derivative of 3x. So we're going to end up with negative 3 sine 3x, okay? And then when we're looking at the derivative of sine 3x, that is going to be 3 cosine 3x, okay? All right, so now we can apply the product rule. So we're going to end up with, I'm keeping my 6 on the outside for now. The derivative of cosine 3x, which is negative 3 sine 3x, times sine 3x. So since we're going to essentially multiply negative 3 sine 3x by sine 3x, that can give me negative 3 sine squared 3x. Okay, and then we're going to add that to the normal first part times the derivative of the second part. So essentially now I'm going to be doing cosine 3x times 3 cosine 3x. So that's going to give me 3 cosine squared 3x. Okay, so that is my numerator, and my denominator is going to end up being 2. Okay, so let's see. I'm first going to distribute my 6 in, and then I'm going to take my limit, okay? So I'm going to end up with negative 18 sine squared 3x plus 18 cosine squared 3x, all divided by 2. Okay, so I'm going to take my limit first. So my limit as x goes to 0. Okay, so if x is 0, that means this is going to be 0, and the sign of 0 is 0. So this is all going to go away because it's 0. So I'm going to have 0 plus, all right, cosine of 0 is 1. So we're going to have 18 times 1, which is 18. And we're going to divide that by 2. So essentially, I'm going to end up with 18 over 2, which in this case is 9. Okay, yay. All right, so we have another indeterminate form that we haven't talked about yet, and that is when we have infinity over infinity. Okay, so now we're going to do some practice where we're going to end up with infinity over infinity, but the process is the same. You're going to apply L'Hopital's rule until you get something besides your indeterminate form of 0 over 0 or infinity over infinity. Okay. So essentially, what you need to think about for this one is as x approaches infinity, this is going to constantly be getting bigger and bigger, bigger, bigger. And in my denominator, the same thing is going to happen. So essentially, what's going to end up happening is I'm going to infinity over infinity. And so I'm going to take the limit. So we're going to end up with, I'm going to take the derivative and then we're going to take the limit again. So we're going to end up with 12x squared. Oops. And remember, you can check in Desmos as well if you are struggling to see where it's going. Minus 6x squared minus 10. All right, so unfortunately, if I'm evaluating the limit as x goes to infinity, guess what? We're still going there. And we're still going there because we still have these x's, and the x's are constantly getting bigger. So essentially, what I'm going to need to do for this is I'm going to need to keep taking the derivative until I end up with no x's. So let's do it again. We're going to end up with 24x minus 12 over 12x. Again, I've still got x's. They're going to infinity. They're constantly getting bigger. So I'm still going there. So guess what? We're going to do it again. So we're going to end up with 24 over 12. And hey, does it matter that x is going to infinity anymore? The answer is no, because now it's 2. Bam, done. Okay. Let's do another one. And this is a trig one. Oh, I thought I clicked the next page, but I guess I didn't. Or maybe I did, and it's still thinking. It's not awake yet. Okay, so for this one, what I did was I checked this one in Desmos, and I changed my settings to be in radians. And I noticed that we were going to infinity over infinity. Okay, so then what I did was I took the derivative. So remember, the derivative of tangent is secant squared. And then I got the derivative of secant, which is secant x tan x. So then I thought, okay, I can simplify this, right? So I know that I can get rid of my secant, and then that would just give me one secant in my numerator. So essentially, I would have secant x over tan x. Now, I don't know about you, but I was remembering the fact that secant essentially is 1 over cosine. And tangent actually is sine over cosine, right? Okay, so now that I have a double fraction, what I'm going to do is I'm going to flip this bottom one. So essentially, I'm going to end up with 1 over cosine times cosine over sine. And then hopefully you're seeing that, hey, I could get rid of my cosines. So then I'm just ending up with 1 over sine. So what I'm going to do now is I could simplify that further, but I'm just going to go ahead. I like sine and cosine better than my other trig ratios, so I'm just going to go ahead and plug in directly pi over 2. Okay, so if you're thinking about this, on my unit circle, pi over 2 is here, and the coordinates there are 0, 1, right? So the sine value at pi over 2 is going to be 1. So if I directly plug in pi over 2, I'm going to end up with 1 over 1, which is just going to give me 1. Okay, so we have two more cases that we're going to talk about. So our life is good when we have 0 over 0 or infinity over infinity, right? So we're just going to take the derivative until it doesn't give us any indeterminate form. Now, if we're looking at this example, this is different because what's going to end up happening here is as x goes to infinity, this is going to go to infinity. But this is constantly getting smaller, 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 smaller. So this is going to go to 0. So what I'm ending up with is infinity multiplied by 0. So that doesn't work for me for L'Hopital's rule. For L'Hopital's rule, we need it to be either 0 over 0 or infinity over infinity. So what we're going to do is we're going to convert it. And I'm actually going to type this because it's going to be faster for me to type it. So what you're going to do is you're going to convert to 0 over 0 or infinity over infinity. And you're going to do that by dividing by the reciprocal. Okay. So what I mean by that is my x squared is the same as 1 over x squared. So I'm dividing 1 by my reciprocal of x squared. And that makes sense because essentially I'd have 1 multiplied by x squared over 1, you'd flip it. And so I'd end up with x squared again, okay? So we're dividing 1 by the reciprocal of this, okay? So what that is going to look like now is the limit as x goes to infinity of sine 1 over 4x squared over 1 over x squared. So that's going to drop to my denominator now. So now what's going to end up happening is we are going to take our derivative. Okay, so this one's going to be a little bit messy because I've got a bunch of fractions and stuff. So essentially, I'm going to need to do my chain rule. Okay, so since we have 1 over 4x squared, essentially I am going to rewrite that as 1/4 x to the negative 2. Okay, so I'm bringing that up just because I like dealing with negative exponents rather than having to do like the quotient rule. Okay, so then the derivative of that is going to be negative 1/2 x to the negative 3. Okay. So you might be noticing something. So the derivative here for this bottom piece is gonna look pretty similar to what we have. Okay, so let's take care of the sine portion of this. So sine, remember the derivative of sine is cosine. So I'm going to end up with cosine 1 over 4 x squared times my u derivative. So that was negative 1/2. I'm going to stick it in the front just because I ran out of room over here. Okay, so negative 1/2 x to the negative 3. All right, now 1 over x squared, remember? That's essentially like me having x to the negative 2, which the derivative of that is going to be negative 2x to the third, negative third. Okay, so now what I'm going to do is I'm going to simplify this before I evaluate my limit again. Chloe. Okay, so essentially, I'm going to get rid of my x to the thirds, and then I'm going to have -1/2 divided by -2, and that is going to give me 1/4. So I'm going to end up with 1/4 cosine over 1/4x squared. Okay, so then essentially, as I'm evaluating this limit, as x goes to infinity, is this is going to be getting to be smaller and smaller and smaller and smaller. So essentially it's going to go to 0, right? So if I'm trying to figure out what the cosine of 0 is, the cosine of 0 is 1. So essentially I'm going to be doing 1/4 times 1, which is 1/4. Okay. All right, let's do one more like that. Okay, so for this next one, we're going to -1, and as I'm going to -1, I'm sorry, 1 from the negative side, that essentially means this is going to go to 0, and this is going to go to pi over 2, and that will be going to infinity. Okay, so I have the same case that I had before happening. Okay, so what we're going to do is we are going to divide by the reciprocal. So in this case, I'm going to use my reciprocal of tangent, which is cotangent. So I'm going to end up dividing by 1 over cotangent, pi x over 2. Okay, so that's going to end up giving me the limit as x approaches 1 from the negative of 1 minus x in my numerator, and this is going to drop down. All right, so now that I have this in a form that I can work with, I can take the derivative. So the derivative of the numerator is not too bad. That's just going to give me -1. All right, now here we have cotangent, and the derivative of cotangent is negative cosecant, and cosecant squared. And the other thing that we have to pay attention to is we're going to end up with the chain rule again for this middle part right here. So the derivative of this middle part right here is going to end up being pi over 2 because the x is going to go away. So for my denominator, I'm going to end up with -pi over 2 cosecant squared pi over x over 2. Okay, so I want to simplify this a little bit just because it's kind of really got a lot going on. So since I've got a negative in the numerator and the denominator, that can go away. Then the other thing that I'm noticing is the fact that if I have 1 over cosecant, so essentially remember 1 over cosecant is just sine. So I could simplify this a little bit, and I could write that sine squared of pi x over 2 divided by pi over 2 on the denominator. So I'm leaving this there, but I'm taking the 1 over cosecant squared and I'm turning it to sine squared just because it's going to make it a little bit nicer. All right, so then we can evaluate the limit as x goes to 1. So as x goes to 1, I'm going to end up with sine squared at pi over 2. And the sine value at pi over 2 is 1. So regardless of the fact that I've got 2 of them, 1 times 1 is going to give me 1. So I'm going to end up with 1 over pi over 2, which essentially I'm going to flip this bottom fraction and I'm going to end up with 1 times 2 over pi. So my final answer is going to be 2 over pi. And I'm done. Yay!